equal to y, uh, uh,
Yeah.
and and by the second equation, we can say
Yeah.
uh, set so y to become 0.
Yeah.
In the first equation, x should equal to y, so I can write it
Mhm.
uh,
X
like
is common. Yeah. Can take
mm,
it out.
r minus 1.
Yep. Plus 0. Yep. So from this,
Uh, from this, we can say that uh, should this the z could equal to this value, or
oh, yeah.
x could be either 0 also.
Yeah, because we are dealing with real numbers. These are real product of two real numbers is equal to 0. That means, yeah, either one of them is equal to 0. Either one of them.
Uh, in here, x I can replace
Yeah.
this
Yeah.
with x, and
Z. Yeah. So,
uh, we can say 0, 0, 0 is one fixed point
yeah.
by looking at the
Yes.
equations.
Yeah.
And if we choose z to be 1 minus r,
Yes.
x
Yes.
be square root
Plus or minus. Yeah. Plus or minus.
uh,
B is positive. Yeah. B is positive.
b to 1 minus
Ah,
r, and y also
the same, right?
the
The
same.
same. All right.
This
Yeah.
is
These.
another fixed point.
Yeah. So we have altogether we have three fixed points. Yeah. Origin and other two. Yeah. The same one. But here make sure that, yeah, so make sure that r is not bigger than 1, otherwise you don't have any roots, right? Complex, because x, y and z are real numbers, so mention that one. Yep. R is less than or equal to 1. Yep. If it is equal, you get the origin. Yes, less than that. That's right. So when r is bounded between 0 and 1, you have three fixed points. When r is bigger than 1, yeah, we have to, yeah, that means we have only one fixed point when r is, because the origin is the only fixed point, right? When r is bigger than, I think so. Yep, I think so. Otherwise, we don't cannot find roots. Yep, I think so. Yep. Yeah, that's right. Well, so those are the fixed points. Yep. So how do we classify those fixed points? Yeah.
Uh,
Yep. Yeah. So, all right, Janitya. Thank you very much. Okay. Well, mm, yeah, there are two ways to Yeah, investigate, classify this stability of the origin, right? So one is that finding the Jacobian for this system straight away. That means the Jacobian matrix is 3 by 3 matrix. Yeah. So you have to complete this as an exercise, right? So 3 by 3 you get 1, 2, 3 lambdas eigenvalues, and investigate these eigenvalues. So whether you have uh, all negative real parts, you can investigate that, right? So do this, right? Complete this. Now at the moment I will follow the book, right? So they so give me a second, right? Give me a second. So I will, for a moment I will stop. For a moment I will stop sharing. Yeah. Yep, here. So here we can consider the linear system. So we ignore the nonlinear parts of the system. That means we can ignore these nonlinear parts, right? Right. Then so we get the simple one for z, right? And we know that this could be, so z dot is equal to negative bz. That means z is equal to, yep, initial point times exponential minus bt, right? So that means z coordinate, as t tends to infinity, z coordinate, everything z coordinate approaches to, yeah, everything approaches to x or xy plane. So that means trajectories, yeah, looks like, so this is x y z. So trajectories approaches, everything approaches xy plane, because so z component decreases exponentially as t tends to yeah, as t tends to infinity. Z coordinate, yeah, decays, yep, exponentially fast, right? So yeah, so then we can ignore the speed from the system, right? And then yeah, then we have, all we have to do, so we have to investigate this one, two, yep, these two equations. So this is how the author of this book did, right? So he considered this one and do that Nisal's one, that is very important, right? So yeah, yeah, so Nisal was correct, yep. So let's follow this method at the moment. Yep. There are two ways, there are two methods. So one of methods is, yep, so ignore nonlinear terms. So then we consider linear system, then investigate the linear system, right? And the other one, you can consider this whole nonlinear one and investigate the Jacobian 3 by 3 and find 3 lambdas eigenvalues, right? Then investigate the real parts of these lambdas. If you have negative real parts, so this is Jacobian at the origin, right? If you have negative real parts, then you have a stable fixed point at the origin. Yep. So do that exercise, right? Do that one. At the moment, let's follow this method here. Yep. Okay. So I hope you understood that, right? Okay, I will stop sharing. Yep, Nisa, go ahead. Tau and delta is the determinant of the matrix, which is sigma minus r. Yeah. So what can you say about the determinant? Yep. Okay. Determinant.
R is greater than 1 uh, for, for a fixed point to define the fixed point, we have this condition.
Yeah, if r is greater than 1, delta is negative.
Yeah.
Delta is negative means delta is remember delta is negative, you have a
Stable
saddle, this side saddle,
yes.
but this saddle is quite different because we are dealing with three-dimensional space. So this is remember, this is delta, this axis, this is tau. So if delta is negative, this side gives you saddle points. Alright, saddle. Okay. So when r is less than 1, what can you say? Less than 1.
R is less than 1. This there is only one fixed point.
So this is negative. Tau is negative, right?
Yeah.
This side. Alright, stable side. Tau is negative when r is between 0 and 1. This one also positive, right? This side. So tau is negative, this plane. So we have to work out this one here. Tau squared minus 4 delta. So compute this. So if it is positive, squared yes. Yeah, so you can do the Nisal's method, right? Nisal do the other method as well, right? Find 3 by 3 Jacobian and its eigenvalues. So analyze those eigenvalues. How do you analyze? Just study the real parts of those eigenvalues. If the real parts are negative, all are negative real parts, then you can say the fixed point is stable. If one of them is positive, then unstable. Yep. So that is homework. Yep. Assign you to do that. So this is looks positive, right? Yeah, positive means on this curve this part is 0, positive, inside or outside? Outside, yeah. So outside.
That means
So
stable.
yeah, stable, yeah. So the origin is stable. Origin and other points are stable because here
There is only one fixed point. No.
there's a
For R less than C one, there is
Yeah,
only one fixed point.
only one fixed point, which is a yeah, which is the so in this range, yeah, the system has only one fixed point, which is the origin. So therefore, in this range, the origin is a stable. No, yeah. So if you do the bifurcation, this is R, right? This is one. You have a so you have a stable. Yeah, origin is so this is R. Uh, uh, what is this? So this axis is R, and this axis, let me, yeah. So yeah, origin. This is X Y. I think yeah, X Y and Z as well. Difficult. How do you draw this? Yeah. So can you? Where is it? Can you?
So only considering X and Y.
Yeah, if you consider X and Y, yep. So let's consider, uh, yeah, let's consider X and Y. Yeah, this is something like this. Yeah. Stable. We have only one fixed point for the system. The origin is a stable. So you have to analyze. So what happened when I is less than greater than 1? So greater than 1, what can you say? For great, yeah, when R is greater than 1, the system has how many fixed points? 1, 2, 3. So this is origin 0, 0, 0, and there are two, yeah, fixed points. Okay, so what can you say about these fixed points? Are they stable or unstable?
Since this become negative,
Okay, yep.
negative, this become so all of these are saddle points.
Standard point, yeah. But so in this case, we are dealing with three-dimensional space, right? So our two-dimensional saddle point is like this. So one is yeah, one is stable manifold, and the other one is unstable manifold in two-dimensional, yeah, case. So here you have X, Y, and Z. So saddle, yeah. So it is quite different from yeah one two-dimensional case. Yeah, saddle. Let's yeah, try to yeah, explain that. Yep. All right, Nisal. Yeah, thank you very much. Thank you. Yeah. So you did a yeah. So good. Make sure that you come. You do that 3 by 3 Jacobian one, right?
Oh, exactly.
Oh, yep. So everybody, so you had to do that. Find the 3 by 3 matrix Jacobian and find all three eigenvalues. Yeah, investigate the real parts of those eigenvalues. Right, study the real parts of those eigenvalues. If the all real parts are negative, then you can say the fixed point is stable. If the real parts are one of real parts is positive, you can say then unstable, right? Okay, unstable. All right, let's yes, slowly, yeah, we discuss this slowly. Yeah, so there's the this one is there is only one x coordinate. So we have, yeah, origin, yeah, 0. This time there is only one coordinate. Yep. So from 0 to 1, you have stable. Okay. So after 1, so we have 3. We have 3. We have 3. Yep. So after 1, the origin becomes unstable, right? After 1. These are what was the origin become unstable, right?
No, so it's
Saddle.
yeah, yes, both. Take it both
What?
together.
Yeah, yeah. I found that. Let me check that. Yeah. So, R between 0 and 1, origin is stable. Bigger than 1, origin. What happened to the origin? Origin. So, what happened to the origin? Origin is unstable, or you calculated delta. Uh, so can I see your workout? Nisal, can you share your delta a little bit? Is it same? Not this one, other one, I think. Yeah. All right, here we go. Yep. Okay. Yeah. So this is negative. So yep, delta is 1 minus r. All right then. Yeah, saddle law unstable. Yep. Yeah. No. Saddle. When but you have to hear, you cannot say like that. So Nisal was right. I think you better to compute 3 by 3 Jacobian, right? Okay. Compute 3, Nisal, compute 3 by 3 Jacobian, right? Then find 3 eigenvalues. So from there, you can say, all right, R, if R between 0 and 1, all the real parts of eigenvalues are negative. When R is bigger than 1, so when R is bigger than 1, so one of, I think one of real parts becomes positive. That means unstable. The origin is unstable after, yeah, when R is bigger than 1, right? Is Does it make sense to you, Nisal? All? Yes, Nisal, yep. Yeah, does that make sense? So you can show that. So first find the 3 by 3 matrix, right? Jacobian matrix. Find 3 eigenvalues, right? Find 3 eigenvalues. All right, are you following me, Nisal? Yep. You are.
I
Uh, yep. All right.
my phone.
Okay, right. So yeah, 3 by 3 Jacobian, right? So find all three eigenvalues. Then investigate the real parts of those eigenvalues. You will see that, all right, when R between 0 and 1, all real parts are negative. That means, yeah, that means the origin is stable, right? When I is greater than 1, you will notice one of real parts becomes positive. That means unstable. Okay.
Okay.
All right. Fine. Oh, okay. Do that. So do that exercise. All right. Thank you. Yeah. So that's why you get unstable. F. Yep. R is greater than 1. Yes. All right. So yeah. So the origin, yeah, fixed point origin. Yeah, if R is bigger than 1, uh, correspond to uniform rotation to left to right. Rotation other side, yeah, rotation. So correspond to non-rotational water. Okay, non-rotation. Left to right, okay, water wheel is changing its direction. Yep, we saw that. We find a fix pitchfork bifurcation. Okay, okay, pitchfork. Yeah, yeah. So if you plot x, yeah, r versus x. This is r. So between 0 and 1 stable, and yeah, r when r is greater than 1 unstable, and you will get new 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 fixed points, a new additional fixed points when r is bigger than 1. Yeah, so this is called, yeah, pitchfork bifurcation. Okay, so if you consider only one of variables, this is x was r versus x, y was x versus r. Yeah, so this is a fixed fork. Yeah, pitchfork bifurcation. Yeah. Alright, but so very difficult to visualize x, y, and z with this variable r. Very difficult to draw, right? Okay. All right. And the other property. So we are discussing the properties of this Lorentz equation, right? So yeah. So this is Lorentz. So like that. Yep. Yeah, Lorentz. Okay. So, and the other property you have this, yeah. So if you make this change to the system, if you use yeah, negative x instead of x, negative y instead of y, so you will see the system remains the same, or it is invariant under this transformation, right? So that means so if this is a solution, you can say, all right, this one also the solution. All right, so you have twin. Yep, so you have two solutions. If x, y, and z, so this point is a solution to the system, and you can say, so negative x, negative y, comma z also the solution to this system. So you found a pair of solutions, right? So all right, so we have this kind of symmetry for this system, right? And the other one is, yeah, volume contraction. Yeah, let's discuss that. So do we have time? 8 o'clock? Yep. So, and what are important things? Yeah, this is very important too. Yep. So volume contraction. Yeah, this one also import. Yes. So this is your, yeah, this is your system, right? So we showed that. So when you vary r bit from 0 to 1, you had only 1 point, one fixed point, which is the origin. So it is stable. Yeah, when you vary this r from 0 to 1, you have only one fixed point, which is the origin. So origin is a stable point. Stable, that means you had a spiral, not spiral, because this is three-dimensional one, right? So very hard to visualize. So this is a three-dimensional one. This is not a spiral. We don't say spiral. X, now we have x, y, and z coordinates. So anyway, the zero, the origin is a stable. So origin is like a sink. Everything going into that origin point. So if you put a, so if you consider a closed surface in this three-dimensional space, and this is your vector field F, right? So this could be, so this could be written in this form. X, vector x is equal to, so this is your velocity field F. Yep. Velocity field, yep. So F is these three, yep. Vector F, right? So this is your field here, right? Okay. So this also, for this range are between 0 and 1. So the origin acts as a sink, or everything going into this hole, this origin point, everything flowing into this origin. Yep. So if you put a surface, closed surface in this three-dimensional space, you have the vectors, yeah, velocity field, vector field like this. So if you put a surface volume, some volume, so you can show that this volume, so you can show that, yeah, you can show that flux going through this volume is decreasing to zero, I think. Yeah, if you put us, yeah, if you put a volume around the origin, so as t tends to infinity, this volume is shrinking to zero. Yeah, yeah, this part here. So the Lorentz equations. So this system is dissipative. That means if you put a closed surface around this, around this, yep, fixed point. Let's say, yeah, this is the fixed point origin. So the volume is reducing to zero as t tends to infinity because of this vector field here. So velocity, that means, yeah, if you consider any, how do we say, any ring of, or any sphere of, so because there's a sink here, everything flowing into this hole, so this is reducing this entire speed, the entire surface is reducing to nothing. Yeah, so this is like a black hole, this is like a black hole, everything attracts to this black hole. Yeah, Yeah, so this is a magnetic field or gravitational field in the space. Yep, everything going inside to this hole. Yep. All right, let's try to show that. So this system, always this system is dissipative. That means if you find that means dissipative means, so you take a point in the space, so you want to measure the flux of this point. So how do you measure the flux density of this space? So how do you find the flux density of this of a particular point? Yep. Anyone? Vector calculus analysis, VCA. So you have done vector calculus analysis. Yep. So how do you measure the uh, yeah, so measure the flux density. Flux density at a particular point. Definitely you have to take the divergence of the vector field. F is the vector field. If the divergence is negative at a particular point, so that means at that point, so that point acts as a sink. That means that point is a sink. So everything going into flowing into the point. So so this system is a dissipative system. That means you have to show that the divergence of this vector field is less than zero. Yep. Yeah, when you find the divergence, so this is the vector field x dot, which is same with f. X dot is f, vector f. This is the field. So when you compute the divergence at a particular point, this is at a particular point. So in the space, if you measure the uh, density of the vector field is negative, that means everything going into the point, particular point. If you take any point in the space, everything going into all our sinks. So this system is a dissipative system, right? So Lorentz system, this system is dissipative because the divergence of the field, this is the field f, vector field f. When you compute the divergence of this field, you will see negative everywhere. So this is true for all points. So here, so x dot, partial of x star with respect to x, partial, which is negative sigma, partial yeah, of y dot with respect to y, which is 1, and partial of z dot with respect to z, which is b minus b. So this is a negative quantity. So for any points, any point, the divergence of the vector field at any point is negative. That means all points in the space are sinks. Everything flowing into the point. Everything flowing in. Okay. So this is a dissipative system. So if you consider a closed surface, so the volume of this surface is decaying to zero or shrinking to zero as t tends to infinity. So you can show that by divergence theorem, I think in the vector. So vector calculus, divergence, that is my next lesson for first year students. Yeah, this week, tomorrow, I will discuss divergence theorem. Yeah, yeah, here we go. Yeah, this one. Yeah, divergence, from divergence theorem. What is this divergence theorem? So if you consider any surface, closed surface, so this is your surface with volume V. So here you have vector field, right? Vector field. So why do we use this? Uh-huh. So divergence, yeah, of vector field. So this is the divergence of the vector of this vector field, right? So this gives you the flux density at a point. So this one gives you flux density of a closed surface. So this gives you flux density across this, yeah, across this closed surface. So if you want to measure the flux density across this closed surface, so you have to use this divergence, this theorem. So this triple integral, yeah, gives you the flux density across this closed surface in the three-dimensional space. So Green's theorem. So this is the theorem, yeah, three-dimensional divergence theorem. Two-dimensional one, remember, yep. So we discussed last week. That's why I remember. Yep. Yep, this one, this is the two-dimensional, this is called, yeah, Green's as second form. Yeah, so there are two versions, Green's theorem. First version is the find the circulation of a closed, a simple closed curve, circulation of a vector field throughout, yeah, along the simple closed curve. So this is the second version of the Green's theorem, or two-dimensional divergence theorem. So this measures, so this needs to measure the flux density across this closed curve C. So this is the three-dimensional one. So this measures, this help you to measure the flux density across this three-dimensional object, right? Okay, so yeah, so this, because this part, this bit is negative, you know that that bit is negative all the time. Okay, so this is the field, velocity field or vector field, right? So this bit is negative, therefore, so therefore from from divergence theorem, so this is negative, this quantity is negative. So yeah, here, so yep, so we can show that. So v dot, the variation of r, yep. So this is the, yeah, Green's theorem here, right? So I will explain this to you. Yeah, so yeah, this quantity is negative. That means, yeah, so the way evolution of this is volume of the closed surface. Yeah, evolution of this volume with time is negative. That means, yeah, v is decreasing exponentially to 0. Yeah, so let's discuss that to 8:30. So let me check. I will cover this and test. Okay, I want to discuss, yeah, this one as well. Yeah, this is very, yeah, this one also important. let me and this is Lawrence work, I think. Yep. I have to finish this up. Yep. Here we go. Here, this is the Jacobian here, Nissal's Jacobian. Yeah. You can find the eigenvalues, three eigenvalues, and investigate real parts. So if they are negative, all are negative, then stay. Yeah. All right. So okay, what was yeah? So global stable. Before that, what was that? Yeah, here we go. Yep. Yep. Volume contraction. Okay. Pick a volume in the space. Yeah, where's that? Yep, like this. Yeah. Yeah, this is a close. So here you have the origin inside. Yeah. So we know the origin is a stable, yeah, stable one. Everything flowing into that origin, right? So pick a closed surface in this three-dimensional space, and this is your vector field, velocity field, right? And this one is the normal, yeah, normal outward vector to the surface. So if you consider this point, and yeah, this is the normal vector to the surface at this point, right? So yeah, this is your velocity field. And how do you find the velocity normal velocity component? So you have to take the dot product with n here, right? Then you get the velocity component, the normal velocity component, yeah, normal outward velocity component, yeah. So which is, yeah, which is f vector field or x dot, yeah, x, yeah, yeah, x del, yeah, x dot, this is the dot product with normal, yeah, this one f dot n. And if you consider infinitesimal time, dt is the infinitesimal time, right? And this is the evolution of the surface. And initial, so this is the surface st at time t, and this is infinitesimal time dt, and this is the evolution in this time interval, right, in this dt time, right? And the movement, yeah, the movement of the surface is, what is the movement? Yeah, so this is the normal velocity component, right? The velocity, yeah, velocity vector dotted with the normal vector, outward normal vector. So this gives you the velocity component towards, yeah, yeah, outward normal velocity component, yeah. And when you multiply this one with the time, the velocity times, that means you get this distance, right? So this is the velocity component multiplied by this time period dt, in infinitesimal time. So this product gives you the distance, yeah, this height. All right. So then the volume of this infinitesimal patch. So this is an infinitesimal patch of the surface. So something like this, yeah. Patch, small infinitesimal patch, right? Tiny patch on the surface. The volume of this tiny patch is, this is the, yep, yep, yeah, depth, yep, this is the area dA. So your volume gives you the product of this. So if you want to find the increase, because of this vector field, velocity field, you could find the increase volume. So how do you find that? You have to integrate. So integrate, yeah, no, double this is the surface, because this surface, yeah, integrate f dot the normal vector dt dA. Yep. So this one here. So they haven't mentioned the double, so this is double integral, right? Because surface integral here, surface. All right. So distance between, yeah, difference between the expanded volume and the initial volume, or general volume, the difference between these two is equal to integral of double integral of this product, right? This one. So you can rearrange this equation. You can divide whole equation by dt, because yeah, the t is an independent parameter. This is the space, and this is time. They are independent. Then you can take out from this operator double integral, right? Yeah, then divide that by, you can take that term to the side. Yeah. All right, so this is the evolution, the volume evolution. So because this is infinitesimal time, right? Very small time interval, time period. So this is approximately equal to the rate of change of the volume of the three-dimensional surface. Right, this side. So we know that the divergence. All right. So now, okay, this one. Okay. Now using using divergence theorem, this one is equal to, remember, yeah, the surface integral is equal to, yeah, this using divergence theorem, this double integral is equal to this volume integral, right? This one is equal to volume integral, diverge using divergence theorem, right? So we know that this we know that divergence of the vector field at any point is negative. Therefore, the rate of change of a volume is negative. That means volume decreases exponentially fast. Yeah, it is decreasing exponentially fast, or shrink exponentially fast. The volume in the space, in phase space, shrink shrinks exponentially fast, right? Because of this, this is negative. So you can separate variables. Yeah, you get this. So this is exponentially increasing to zero as t tends to infinity. Yep. Therefore, volume is contracting or shrinking exponentially fast. Yeah, to zero. Yep. So it eventually shrinks to the volume becomes zero. That means, yeah, shrink to a limit set of zero volume, like a balloon, right? So yes. So yeah. So contraction too strong. So this one gives you an idea about the field, the solution space. So everything, yeah. So when when you vary r in between 0 and 1, so this the origin acts as a sink. Yep, everything flowing into this point. So that means the solution curves does not go away from the origin. So everything, yeah, everything, yeah, attracting this the origin. That's why attraction strong constraint on the solution of the Lorentz. Yeah. So we can show that there are 37, 35. Yep, we can show that it is impossible for Lorentz system to have either repelling fixed points. Uh, yes, so if you keep a closed surface around the origin, repellers are sources. Yep. Uh, so no, yeah, there are no repellers in Lorentz system. I think. Yep. So you this yeah, so close of repelling close of its possible for, but what happen when r is greater than 1? So r is less than 1 is okay. When r is greater than 1, so we have a saddle point. R is greater than 1. R is greater than 1. Yeah, be sinks. Or fix. Yeah, or fix. Or saddle. Alright, anyway, so let me check. Let me. Uh, okay. Yeah, so we showed that when r is less than 1, the origin is a sink, or that means it sink means attract. So we can show that there are no repellers when r is less than 1. Yes, possible to have repellers, right? When r is less than 1, so we have origin is the only one, so it is an attractor, right? So we can show that attractor is globally stable. That means all trajectories come down to the origin. That means origin is a real sink. So this is a sink leak. Yep, there's a hole like that. So we are going to show the origin is a global stable whenever r is less than 1. So for that you have to find a Lyapunov function. So you have to construct a Lyapunov function, right? So you know that there are no proper methods to construct Lyapunov or any energy function, right? So I think better consider the sum of square, then most of the time that works. So if you consider sum of square of these variables, state variables, most of the time it works, but you have to adjust these coefficients, right? So I will get, yeah, so author, this author, or Lawrence, yep, Lawrence, consider this, yeah, this function. So we can show that, so this is, it's a positive definite function, yep, because it is sum of square, this is a positive constant here, right? So at the origin, this becomes 0, the this function becomes 0 at the origin. So other points, it is positive all the time. All right, so this is a Lyapunov function, and to show that this is a Lyapunov function, so you have to study the evolution of this function. So yeah, so for that you have to differentiate this with respect to time, to say, to find, to study the evolution of this function. So let's differentiate that function with respect to time. Right. So then you get, yeah, you can rearrange this equation. You can completing squares, b square, right? So anyway, so this is the variation of that function. So you will see that this is negative whenever this is negative for all, except this is negative, this is negative except the origin, right? Or when I is, yeah, when I is less than 1, definitely, yeah, this is negative. I is less than 1 and this coordinate is not equal to 0 0 0, then this is strictly negative. That means, so this surface, this not surface, it is an object in 4-dimensional space, because there are 1 2 3 independent variables with the dependent variable v. So this is 4D function, right? 4D function. So yeah, so this, that function, yeah, that function, that surface, that not surface, it's a 4D object in 4-dimensional space. So that one, that surface is reducing with time, reducing with time, because the way evolution of that function is negative here. This is the rate of change of that function with respect to time, right? So as t tends to infinity, that function, yep, yeah, that function, so something like that, that that fun, yep, that fun, that, yeah, surface, if you consider the surfaces in 3-dimensional space, so if this is constant, right, so then this is a surface, right? So as t, when you increase time, this surface getting smaller and smaller, and what happened, and as t tends to infinity, the surface becomes nothing, uh, becomes nothing, right? Decreasing to 0. Yeah, yeah, decreasing to 0, it vanishes. No, yeah, yeah. So therefore, from, yeah, Lyapunov. So this is v is a Lyapunov function, right? Positive definite, and we at the origin is 0, yep, and the evolution, the rate of change of this function is negative, strictly negative for all values except the origin. along any trajectory. Therefore, the origin is a global stable point, right? So we can show that, yep, the origin is a global stable point whenever r is less than 1. We know that r is greater than 1, origin becomes unstable. So origin is not only stable, but it is a global. That means all points, all curves, all trajectories collapse down to the here. If it is a global stable, all trajectories attracting to the origin for this values, for this r parameter also. So do you have any questions? Any? Yep. Yeah, this all and all. Yep. Any questions? Any doubts? I think this part also very important, right? So make sure that you study that three dimension, yeah, a 3 by 3 Jacobian matrix. Find, yeah, investigate real parts of all eigenvalues, right? And and yeah, so yeah, we can show that, yeah. So when r is less than 1, the origin is stable, right? When r is greater than 1, origin is unstable, and when r is less than 1, the origin is not only stable but also it is globally stable. So from this can find a Lyapunov function. Okay, find an energy function like this. We show that because by investigating the evolution of this energy function, we came to conclude that this origin is not only stable but also global. That means all trajectories uh, come to the origin. Yeah. So these are very important lessons, right? So let me see. And the other one here, when r is greater than 1. Okay, so we know that when r is greater than 1, origin becomes unstable, but we have another two. So r is greater than, this is 1, r, this is 1, right? When r is greater than 1, origin becomes unstable, but the system generates two two stable limit like two stable fixed points. Yep, I think, yep, you can I think, yeah, exist, yep. Can show that this stable, yep. So at this, so this is Lawrence work, right? He found, so these are not important because we don't have so enough time. So this is Lawrence work. Okay, so he found a number. So r, so here r is greater than, yeah, greater than 1, and between this special number here. So he found a number here. So at this point, so at this point, at this value, yeah, so there is a subcritical hub bifurcation happen at that point. So don't worry, so because of the limited time. So this is subcritical. So this is stable and this is unstable. So here look at this. This is our saddle point. So we know that at the origin we had a unstable saddle point, right, at the origin. uh, Remember, yeah, when I is bigger than 1, so we had, yeah, step two fixed points, additional fixed point in the system, and this origin becomes unstable. And what happened, Janit, or Isir. So when I is bigger than 1, then delta was negative, right? Delta was negative. That means saddle. I don't remember that. Yep, delta was. Let me go back. So what was the delta? Delta that simple. Yeah, this one here, delta. Is bigger than origin is saddle. Alright. Origin is unstable or saddle point in 3 dimension. Yep, unstable. This is a new type of saddle for us. Yep. So here, so this is, so when, so this one is R. Yeah, this is for R bigger than 1, less than R sub H, R hub bifurcation. So at this point, Lorentz discovered that, so system has hub bifurcation. All right, so that is all right. So we don't know that much, right? So this is a particular number. He found this number. So at this point, so yeah, hub bifurcation occurs at this point, at this parameter value, right? So this is yeah. So when r in between 1 and this particular value, right? So origin is a saddle or unstable or saddle point. So this is the unstable manifold, right? So this is a kind of new to us, right? So yeah, so this is I think we cannot visualize the stable manifold. So this is unstable manifold because here this is the saddle cycle. So here we are dealing with three-dimensional flows. We investigate the dynamics of three-dimensional systems. So very hard to visualize, but two-dimension we could identify stable manifold and unstable manifold very easily. But here very difficult to visualize everything. So this plane gives you the unstable manifold, very hard to visualize, right? This plane, this infinite plane. So on this plane you have saddle cycle like this. So we have limited time, so we don't have much time to explain this all, right? So three-dimensional, I think you better to investigate the that 3 by 3 Jacobian matrix and find, yep, find eigenvalues and investigate the real parts of those eigenvalues, and you can show that, yep, all have negative real parts, whenever r is less than 1, that means the origin, yeah, origin, when r is less than 1, there is only one fixed point in the system, which is the origin is fixed, which is stable. So from this part, Lyapunov part, energy function, so we show that it is not only stable but also it is globally stable, right? Yeah. Yes, that, yeah, from this function, yeah, by finding a function like this, so we showed that 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 origin, we know in this region, yeah, in this, yeah, the origin is stable. We show that it is globally stable. All right, that is important, right? That means, so that means if you consider any close, yeah, so this is three-dimensional space. Yep. So origin is a global stable. That means, so if you choose, you could pick a sphere in this three-dimensional space. So you can, yeah, you can say that, all right. Okay, so that means if, yeah, that is globally stable. So everything at track, everything, all trajectories, yep, come down to this hole. There's a hole here, origin, because it is globally stable. So when something, some trajectory enters into this sphere, it does not leave. It does not leave. It does not leave. It is confined to this sphere. Yep, it does not leave this sphere, so because it is globally stable. I think these things are very important, right? These things are very important. Don't worry about. Yep, I think get it. I think if you have time, better to investigate these hub bifurcations, right? But yeah, yeah, limited time, so we couldn't discuss many examples. Yep. So and finally we showed that if you have a surface like this, because of this field, so this point is so there are no repellers, so this is globally attractive, right? So if you put something, if you consider closed surface, so it is shrinking to zero. That means, yeah, that means, yeah, that means, yeah, these traject, yeah, if you consider any closed surface, yeah, this consider a particular trajectory or any trajectory. When this trajectory enters into this surface, it does not leave the surface. It does not leave, yeah, it does not leave from the surface, and it is that one settle down an object and its volume is zero. So that is the, yeah, that is the summary of the work, I think. Yeah, so it is that trajectory settling down on something where, yeah, so if you can, yeah, so and that curve, or not a curve, it is not a curve, it is yeah, the dimension of that not surface, we cannot say it's a surface, a dimension of that object is between 2 and 3, If you have time, better to investigate that. So what I want to mention, yep, is yep, do this, find lambdas, investigate the eigenvalues, and this one is important. Show that it is dissipative. Then take close surface and show that it is decreasing to zero, and yeah, and we showed that and zero origin is a global stable. Then we found it constructed an energy function like this. We show that this the origin for this scale, yeah, the origin is globally stable for this scale, right? Yeah, that is very important, right? So this is what I want to say. Yep. Right, I hope so this is very important for your exam next week. Yep, let's discuss other three other, yeah, related to it. So this is, so I will give you one of problem, yeah, problems from this part, three-dimensional part, and let's discuss another, yeah, couple of questions yeah, next week, right? So we done, we covered everything, right? We covered everything. So so with the limited time period, I think we are done. Then now you are ready for the exam. Next week, let's do some revision. Let's brush up our knowledge on those things. Yep. One dimensional, two dimensional, three dimensional is okay. Yep, this one we covered three dimensional part. So do those homework, right? Was assigned to you, right? So do those things, very important, and let's discuss next week. All right, thank you. Do you have any